มนุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำเร็จที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้า
Okay. All right. Okay. Good afternoon, everyone, and welcome to EVE Colloquium Online Seminar Series number 15, organized by the Institute for Fundamental Study in Naresuan University, Thailand. My name is Siklin Yukong. I am EVE Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon online event. For this talk, we have Korkeathikhun from Department of Mathematics, National University of Singapore, to talk on a topic and exposition of quantum groups and quantum symmetric pairs. Let me spend a bit more time to introduce our speaker formally. Korkeathikhun complete his bachelor degree in mathematics from Department of Mathematics and Computer Science, Faculty of Science, Chulalongkorn University, Bangkok, Thailand. And then he continues his Ph.D. in mathematics at Department of Mathematics, University of North Carolina at Chapel Hill, United States of America. Currently, he is a research fellow at Department of Mathematics, National University of Singapore. His research interests are real algebras, quantum groups, and their representation. Okay, the talk will be roughly 40 minutes long. Before I stop during the talk, if you have questions, you can put them in the comment. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give the screen out to our speaker, Korkeathikhun. Okay, screen is yours. Okay.
All right. Thank you so much, Professor Sinkarin. I'm very happy and very excited to be here and very grateful to having me today. And all right, let me share my presentation.
Okay.
Yeah. All right. And also thanks for warm welcome. Yeah. And it is my first time to present my work outside my mathematical society. Yeah, actually.
Oh,
All right.
okay,
And
okay.
I try to do the best so that the audience here
Me too. I will try my best to listen to you.
Yeah, all right. And I would like to put my disclaimer here because I'm a math person. I do math so far, and I really don't understand what I'm doing to do in terms of physical meaning. So, which means that I probably not be able to answer some physics questions. Sorry about that in advance.
Oh, that would be fine. I think, yeah.
Okay. Yeah. All right. Okay, let me start. Okay. So I would say that it is kind of crash course or lightning introduction to the quantum groups and quantum symmetric pairs. And as you know that the terminology quantum appears, in many contexts. But in this context, I will try to explain what is the term quantum or quantization, through math. And all right, let's start. Right. Okay, first of all, a quantum group is not a group. Okay, a term group right here, it is the term in sense of abstract algebra, but I will give you a pretty much precise definition of the quantum group. Okay. And a quantum group appeared first time in the work by Drinfeld and Jimbo, and they work separately, independently, and it appeared in the study of the theory of quantum integrable systems. Okay. And at that time, I think there is a equation called quantum Yang-Baxter equation, and so far they try to solve this equation, to find a solution to this equation. And for the classical equation, I thought that people try to find the first order approximation, but to find a precise solution, so Drinfeld and Jimbo, construct a solution to this equation using the quantum group. Okay, and this arises from the two-dimensional solvable lattice models. All right. And in their work, they introduced a quantum group as a class or family of Hopf algebras, which is deformations of universal enveloping algebras I understand that in the beginning of their work, they work on the SL2 Lie algebra SL2 case, and then they generalize to the Lie algebras and then to the more general Korkeat algebras. And no worries, I try to give some definition on the Lie algebra and universal enveloping algebras and so on. All right. And the study of quantum groups has been observed so far, and it relates to many areas of study, such as statistical mechanics, conformal field theory, knot theory, and etc. Right. And from time to time, it was used in the language of the physics, but after that, some mathematicians tried to reformulate this study using the language of Lie theory. Right, and this is just a brief history of a quantum group. All right. So, okay, first of all, let me give a very quick review what is group, field, and so on. All right, and first of all, a group is just a set. Okay, imagine it's a set. It can be finite set or infinite set, and it comes with a binary operation called star on the set G. Satisfy the following properties. So the first one is the associativity, which means that you can, if you have A times B times C, it means that you can multiply AB first or BC first. Yeah, they are equal. And also it has the identity elements, and every element has inverse. All right, this is the definition of group. And secondly, a field. All right, a field is just a set. It could be finite set or infinite set, okay? But for the field, it equipped with two binary operations called one is addition, the other one is called multiplication on the set K, such that addition and multiplication satisfy the associativity and commutativity. And also, it also has an additive identity and multiplicative identity called 0 and 1. Also, under the addition, every element has an inverse called, for any element A, there exists the unique element B such that A plus B equal to 0. And basically, we call this B minus A. But for the multiplicative inverse, we just require that every non-zero element has the inverse. So it means that for any non-zero element A, there exists unique element B such that AB equals to BA equals to 1, right? And basically we call this B use the notation A inverse, which is the makes sense notation because we are talking about the multiplicative inverses. Okay, and the last one is the distributivity. Is it just does the intertwine between the addition and multiplication. Yeah, and this is the definition of a field, right? So the next term is algebra. Okay, so it is simple. So algebra is you start with a vector space called A. Okay, the vector space over a field K, and you just equip this vector space with a bilinear map. Yeah, basically it means that you are going to define the multiplication on the vector. Okay, and finally the term group algebra, it is you start with a group G. Okay, and the group algebra is an algebra whose basis is the element in G. Okay, and you just extend the multiplication on the group to the multiplication on the algebra, and basically the elements of the group algebra are the formal sum on the group G. All right. Okay. So as I introduced in the beginning, that I would show you some notion of the quantization of deformations. So here are some examples. The first thing is the Q integer or Q binomial coefficients. So right here, I let Q be an indeterminate value over the rational numbers. And for each integer n, the Q integer is defined by, use the notation bracket. And if you read some textbook, sometimes they put the subscript Q below the bracket to indicate that it is a Q integer. But right here, I just use the bracket n. So I define the bracket n to be this fraction Q to the n minus Q to the minus n over a Q minus Q inverse. Okay, and right here you may think that you start with just an integer n, right? And to define the Q integer, you just attach a new parameter Q in some sense, but the way to put parameter Q is it must behave in a nice way, and which I show you how nice it is, right? And the next thing is for each integer m and n, the Q binomial or Gaussian binomial coefficient is defined by this bracket. Actually, the notation looks like the m choose n in the combinatorics, and it defines to be like bracket m times bracket m minus 1 and so on to bracket m minus n plus 1 over the bracket 1 times bracket 2 blah 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 to bracket n. Right, this is the definition. And finally, we define a factorial of this n for any non-negative integer by we define the factorial of bracket 0 to be 1 and the factorial of the bracket n to be this quantity. Yeah. It is actually really analogous to the factorial of the positive integer that we familiar with. All right. Okay, and as I said, you can prove yourself that for any non-negative integer m and n such that m greater than or equal to n, so you can show that m bracket m n here equals to m factorial over n factorial times m minus n factorial. Yeah, this formula very much looks like the m choose n. Yeah, right. Yeah, and even if you look at the definition of the Q integer and Q binomial, you may think that it is just a fraction, like the rational function, but it actually you can prove that Q integer and Q binomial is just a polynomial ring over integer with the variable Q and Q inverse. And the one thing that I want to point out to show what kind of the quantization or deformation is that if you look at the definition of the bracket n, So then take the limit q goes to 1. So you just use the basic calculus you learned from the first year university. It is a little bit, it is the indeterminate form, but you can use the L'Hopital so that you can show that this bracket n approaches to n, and this Gaussian binomial becomes just the m choose n when we take the limit q goes to 1. So this is the first example of the notion of deformation or quantization of the classical object we know. Okay, the next thing is a little bit more complicated, and I'll try to describe very slowly. So it is the Iwahara Hecke algebras, or people call in short Hecke algebras. So we start with a symmetric group Sn here. So recall that the symmetric group is just the set of permutation of an object. So you may think that it is just the permutation of the number 1, 2, 3, and to n, and the element of the group is just the permutation. And it is known that this group can be generated by S1, S2 to Sn minus 1, where Si is the permutation between I and I plus 1, right? And right here, it is the group algebra, which means that it is an algebra. It is a vector space, yeah, and the basis is the element of the symmetric group, and then the element of this algebra, group algebra, is just the formal sum here, and then you extend the group multiplication to the algebra multiplication in the natural way, right? So yeah, this is the group algebra of Sn, and the Hecke algebra denoted by this script h of the group Sn. It is the algebra over the ring of polynomial over integer with a variable q and q inverse, and this algebra comes with a unit of the unit under the multiplication, and this algebra generated by notation Ts, and this S range over the element of the symmetric group Sn, and this generator are subject to the following relations. So the first one is called the quadratic relation, and the other two equations are called the braid relations. All right, and okay, and what happens if we take q equals to 1, for example, and so look at the first equation here. So if you take the q equals to 1, you have that TSI square equal to 1, right? And nothing happens to the second and third equation because there is no q. And anyways, and then if you identify TSI and SI, you can see that H specializes to Sn again. So it should be the group algebra of Sn, not Sn, right? Okay, for example, you have TSI squared equals to 1, right? But for the SI itself right here, because it is a permutation between I and I plus 1, right? If you multiply them, SI squared, you get the identity I, right? So which means that you can say that Hecke algebra is the deformation or quantization of the group algebra of Sn. And the Hecke algebra specializes to this group algebra when you take the q equals to 1, right? Okay. And all right, and the next thing is about the last example is the quantum group of SL2 case. Okay. And so first of all, let me introduce the universal enveloping algebra, which I denote UEA, of the Lie algebra SL2. So it is an associative algebra over a field of complex number with the unit and generated by 3 elements, E, F, and H, and this subject to three conditions here. And if you guys know the Lie algebra of SL2, you will see that it is actually the relation actually similar to the Lie bracket, because you have the E bracket E and F equals to H, and bracket E, the bracket H and E equals to 2E, and the bracket of EF equals to minus 2F. Yeah. But okay, by the way, this is the definition of the UEA of SL2. And the quantum group of SL2, okay, again, when you say the word the quantum, it means that you are going to put another parameter Q, and you basically quantize the UEA. So the quantum group is and again, associative algebra over the field of a rational function with a unit 1 generated by, again, 3 generator E, F, and Q to the H. Okay, it is just simple, subject to the following relations here. And if you compare the conditions on the UEA and the quantum groups, you may see some similarity here. For example, the first relation and the first relation of UEA and the first relation of the quantum group, it almost it's not the same, but you can feel that, yeah, this kind of quantized of the first one. The second one is the kind of the quantized of the first one. Anyways, what if I take the limit of the right hand side of the EF minus FE equals to Q to the H, blah blah blah. What if I take the limit of this quantity, or Q goes to 1? Yeah, you get a H, right? And then the first relation becomes to the classical one. I mean the relation of the UEA, which is EF minus FE equals to H, right? And what about the second relation? You have the Q to the H times E times Q to the minus H equals to Q squared times E, right? And if you just replace Q by 1 directly, you get nothing, right? You just get E equals to E. But if we do a little bit tricky, by differentiate with respect to Q, both sides of the equation, just basic calculus, and then you take the limit Q goes to 1 again. So eventually you will get HE minus EH equals to 2E, which is the second relation of the UEA again, right? And you can do the same thing for the last relation, right? And so, yeah, so you can roughly say that a quantum group of SL2 specializes to the UEA of SL2 when you take the limit Q goes to 1, all right? And with those examples in your mind, we may say intuitively that a deformation or quantization of a given algebra A is a families, or it is a family of some algebras, depends on the new parameter Q in the nice way, such that when you take an appropriate Q equals to certain appropriate certain number, that family should give you back the original algebra A again, right? So, and this is the introduction of the notion of the deformation and quantization. So, any questions so far? All right. So, okay. Any questions?
No,
Okay.
I don't think so. Okay, you
Right.
please continue.
Okay, so all right, the next section is I'm going to give a precise definition of the Lie algebras, universal enveloping algebras, and their representation, and so on. Okay, for the Lie algebras, you start with a vector space okay, I call this notation G over a field complex number. But in general, you can work any kind of field. You can even work on the field of real number or finite field, like the field of integer modulo prime number, something like that. And this vector space comes with an operation which is called the Lie bracket. Right? And this vector space will be called Lie algebra over C if it satisfies the following axiom. So the first one is bilinear, which means that it is linear on each component. Secondly, the bracket of the same element equals to 0, like the bracket of x is equal to 0. And the last one is satisfy the Jacobi identity. Right? Okay, for example, for the trivial case, you can make any vector space Lie algebra because you can just define the Lie bracket equals to 0, right? But this is boring. This is nothing interesting. Yeah. And secondly, it is you have known so far, but maybe you don't know it has a Lie algebra structure. It is just the R3 with the cross product, right? So it has a bilinear, and you take the vector in R3 cross itself equal to 0, and it satisfies the Jacobi identity, right? And the last one is pretty much the standard example. So it is just a set of square matrix of size n by n with the bracket defined by the commutator. Right? It is the bracket of AB equals to AB minus BA. Right? And you can check that it satisfies these three properties. Yeah. Right. And actually there is a classification of simple Lie algebra. I mean, for the simple Lie algebra, I mean that it is non-abelian and there is no proper sub-ideal. Right. Okay. And there are 4 classical types of the Lie algebra. Okay. And there are 4 types, which is type A, B, C, and D. Okay. For the type A, yeah, it is the set of matrices, square matrices of size n by n. In some textbook, they just use the notation like the third example right here, MAT. But some textbook use this font math frac GLN. And I think that the reason they use this one because they want to remind themselves that the Lie algebra is just the tangent space at the identity of the Lie groups. Yeah. So because it is so for the Lie algebra SLN here, you just take you think of the Lie group, it's a special linear group, yeah, and then you take the tangent space at the identity, so it becomes a Lie algebra of type A, and it is the same to type B, C, and D. I mean, it is actually true for any Lie groups and Lie algebra. Yeah, you can take a look further in the Lie theory, okay, but one can describe the element of the Lie algebra in a very, very precise way as a set of matrix. So for type A, it is just a set of square matrix that trace equals to 0. Okay. For the type B, it is just a matrix of size 2n plus 1 satisfy this equation. Yeah, when S equals to this matrix. Alternatively, you may think that the Lie algebra is just a set of matrices that preserve under a certain non-degenerate bilinear form, and that the non-degenerate bilinear form is just determined by this S. Yeah, right. Okay, right. Okay, that's the definition of Lie algebras, and the next thing is about the universal enveloping algebras, which I denoted by UEA of the Lie algebra G. So by definition, it is a pair U of G and I, and the U of G is an associative algebra with 1 over a complex number again. So I mean, in this talk, I will talk over only a complex number, and this I is the kind of the linear map, from the Lie algebra to this algebra, satisfy the following property. Okay, it's kind of intuitively, it's kind of to just change the notation, the bracket, to the xy minus yx, which is more pleasant to work with, because multiply them naturally is much handy in work, right? And also satisfy the universal property. And by the universal property, it can be proved that such a pair is unique up to isomorphism. Okay. And all right, there is a standard construction of the UEA. So I mean, given a Lie algebra G, and then you take the tensor algebra over G. I mean, recall that Lie algebra, it is a vector space, right? You can define the tensor algebra on it, and then you quotient by this ideal J that is generated by this element of this form, x tensor y plus y tensor x equals to a bracket x and y. Or alternatively, you may think that you are going to identify x tensor y, y tensor x plus y tensor x equals to the bracket x and y, right? And then this quotient is it is the universal enveloping algebra of G, and the map I, basically you just take the restriction of this UEA. I mean the restriction in the tensor algebra to the UEA of G. And anyway, if you feel that it is still sounds abstract, you may think very, very roughly that so UEA is just the maximal associative algebra over C with one. So you have the Lie algebra G, right? And you have the universal enveloping algebra. And the map I means that the UG just cover this Lie algebra again. And that such an algebra is the maximal one, right? And such that the element of the UG, you just let generated by the element in G in a natural way, and then you put a condition that x times y minus y times x equals to bracket x y. Right? This is the natural way to think of the UEA. Right? And this is the famous theorem called PBW from Poincare, Birkhoff, and Witt to describe the property of this UEA. So the first one is that the I that come with the UEA is injective, which means that you can really think that the Lie algebra can be embedded into the UEA. And secondly, if you have an order basis on the Lie algebra G called X alpha, okay. So the second statement says that UEA has a nice basis, right? And the basis is of this form. You just multiply them and put in the order from the order of the basis of G, and this form together with one form a basis of this UEA. Yeah. All right. Okay. Right. Okay. Let's look at the example on the SL2 case. So for the SL2 case, there is three generators, right? E, F, and H. And recall that the SL2 is the set of a square matrix of size 2 by 2 that trace equals to 0. Okay, and as a vector space, they are three bases E, F, and H, as I described here. And you can compute yourself. It is just the matrix multiplication that the bracket of HE equals to 2E. But basically, it is equals to HE minus EH. You can check that it is equals to 2E, and so on. You can check yourself. And by PBW theorem, a basis of the UEA of SL2 are in this form. Right? It is a pretty nice description of a basis of a UEA of SL2. All right. And this is about the UEA. And the next step is that we are going to quantize the UEA. Again, the quantize means that we are going to put a parameter Q and let it flow, and then it means, and we expect that if we take an appropriate Q to appropriate value, we should get the UEA back again. All right. And from the work Drinfeld and Jimbo, they introduced the quantum group of a semi-simple Lie algebra and Korkeat Lie algebra as a quantization, as a half algebra of the UEA, right? And then it can be proved that this quantum group specializes to the UEA when we take Q equals to C, when we take Q equals to 1. All right. Right. And here I put some reference here. The first two reference, I realized that it is the origin of the quantum groups. From the work by Drinfeld and Jimbo. As I said that they work separately, but they kind of give the solution to the Yang-Baxter equation. And for the three reference, Jensen, Hong Kong, and Lustig, it is just the basic and the definition of the quantum groups, if you guys are interested in. But it introduced in terms of Lie theory itself, using the language of Lie algebra, root system, and representation, and so on. But it is there are still good references. All right. I didn't give you a precise quantum group of any Lie algebra or Korkeat algebras, but let me show you a small case, which is the quantum group of the SL2, and I'll show you some of representations of it, right? And okay, let's start with a indeterminate value Q over the complex number, and right here suppose that Q not equal to 0 and Q squared is not equal to 1 to avoid the complicated situation. All right. So, and the quantum group or the quantized universal enveloping algebra of SL2, and right here the notation is pretty much natural because I just put the Q right here to remind that you just quantize the UEA of SL2, and by definition it is the associative algebra over C with unit 1 and generated by 4 elements E, F, K, and K inverse satisfy the following relations. And again, you see that in the relation you get Q right here, and if you compare to the definition of I mean the relation from the Lie from the UEA, you see some analogy between these relations and the relations from the UEA. Okay. Right. And there is a fact to show that there is a nice basis of this quantum group of SO2. So the basis is in this form. Pretty much looks like the basis of UEA of SO2. All right. And quantum groups have a rich properties. The one is that it has a half algebra structure. Okay, and right here, let me just assume that it is the quantum U is a quantum group of SL2. All right. So for the half algebra structure, it is given by the following. So you have the coproduct called delta, which given by this tree relation. But basically you define a coproduct on each generator of the quantum groups K inverse E and F, right? And then you extend it algebraically. And then we need to define the co-unit, and the other one is the antipode S, right? Actually, it can be. I mean, it is true for any Lie algebra or Korkeat algebra, but the definition is a little bit more involved because that would involve with the root system of the Lie algebra. And but anyway, to define the coproduct, co-unit, and antipode are similar. Okay. And the one point is that if you go through different textbooks, I mean, my point is that it is not a unique way to give the half algebra structure. which means that there is no unique way to define coproduct and antipode. If you look at different textbook, they would give a different definition of coproduct and antipode. I mean, both of them can form a Hopf algebra structure, but they give the different convention and notation. Yeah, just if you're gonna work with quantum groups, yeah, just keep in mind that you use the one that consistent along your work. All right, and there are a few important representations of this quantum group, and the first one is the adjoint representation, which define, again, it is enough to define only on the generator of the quantum group, which is K inverse E and F, and this is the definition of the adjoint representation, and again, it can define. It is also be able to define to any Lie algebra, not only the SL2 Lie algebra. And the other one is the standard representations. So for SL2, we start with the vector space over C with the basis V minus and V plus. And we define the action by, so I take K act on V minus equals to Q V minus, and Q act on V plus equals to Q inverse times V plus. And we define the action of E and F as shown in this diagram. So if I would say that I take V minus is the highest weight vector. So you can say that E is the raising operator and F is the lowering operator. You see, because V plus is the lower one and V minus is the highest one. Then E, the operator E, is just take the lower to the highest one, and then if you take E again, it vanishes. All right, and it is similar to F. F take the highest to the lowest, and then if you take F again, you just vanish the lowest one. Right. So yeah, and this is the standard representation. Right. So all right, and that's about the quantum group. UEA and about on the SL2 case, but again, it is also true for any Lie algebras. And the next section is I'm going to talk about the quantum Yang-Baxter equation that I said in the beginning, that they construct a quantum group to find the solution to this equation, right? And first of all, let me recall what is the quantum Yang-Baxter equation. And start with the finite dimensional vector space V, right? And I let R be an endomorphism of V tensor V, any endomorphism, okay? And define an endomorphisms R1, 2, 2, 3, and R1, 3 on threefold tensor product V tensor V tensor V by the following. So R1, 2 just, R is the endomorphism on V tensor V. So R12, you just act the identity on the third one, and then you take R on the first two V. And for R23, you just fix the identity. You just act trivially on the first component, and then you take R on the second and third V tensor V. And for the R13, it is not natural. You just fix the second one, and then you take R on the first and the third one. But it is a little bit more tricky. But it is defined this way. So P is the permutation. You just permute U tensor V equals to V tensor U, right? Okay. And the equation R13 times R13 times R23 equals to R23 times R13 times R12. And this equation called quantum Yang-Baxter equation. All right. And this equation was introduced independently by Yang and Baxter, right, in the study of statistical mechanics. And it is used to describe the 6 vertex model. And honestly, which I try to understand what it is. It is really physics. And all right, and a solution to this equation, is called R matrix. Right. Okay. And as I said that a Yang and Baxter find the solution to quantum Yang-Baxter equation, as a first step on the SL2 case, and then any Lie algebra, and then Korkeat Lie algebra. And yeah, for SL2 case, this is the solution to the quantum Yang-Baxter equation. Yeah, and it is the infinite sum and some exponential right here satisfy the certain property here. And if as an endomorphism on V tensor V, just recall you. But if you want, you can think that R is an element of the completion of U tensor U. That's the other way to think of. But in a natural way, you just think that R is the endomorphism. Yeah, and even though you see it is the infinite sum, but when you act on the finite dimensional vector space V right here, it means that for the large term it will vanish. So only finite term survive to act on the V tensor V. Right. And later, Lustig construct in such an element are in a more general, but also more conceptual way. But if we use the Lustig construction, it looks simpler when we consider on the SL2 case, which I'm going to describe in the next slide. Right. So okay, and here is his construction. So for any non-negative integer n, he defined the theta n looks like this. Yeah, it is actually looks like the term in the parentheses of this R, but in his expression he avoid the exponential term. Yeah, and this is his one, and then he put define theta equals to this summation sum all over n here. And this theta is called quasi-R matrix because it is not the solution to quantum Yang-Baxter equation yet. So yeah, and again, you regard this theta as the linear map on the tensor product of the finite dimensional U module or representation of U. Okay, right, and I will try to skip the detail above, but here is the theorem that it is proof that this theta composed with this F tilde is the solution to quantum Yang-Baxter equation. Right? And this F tilde is kind of weight function that you weight the vector M tensor M prime, and this function F lambda mu is it is a function on the weight and satisfy a certain relation. It can be proved that such a function exists. All right. Yeah, and this is the I don't know if you can say that it is the cleaner way to find a solution to the quantum Yang-Baxter equation. Yeah. Right. Okay, let's look at an example. So again, let me put M and M prime be the same, and it is the standard representation of SL2, quantum groups of SL2, and with the basis M minus and M plus, and this is the with the standard representation, this is an action of it. Right. And by the definition of theta n, so we have that theta 0 is 1, theta 1, act on M minus tensor M plus is in this way. And I actually don't care the theta 2, theta 3, and so on, because if we take the theta 4, 5, 6, and so on, you have F to the the higher power, and the higher power does vanish everything here. It means that it is enough to look at the theta 1. Yeah, that's enough. Yeah. Right. And again, I choose the appropriate the weight F that satisfy the certain condition in the previous slide. All right. And yeah, and I write it in the matrix form with respect to this basis, M minus minus, minus plus, plus minus, and plus plus. and the first metric is and the matrix theta, and the second metric is the F tilde, and you can check yourself that this matrix is the solution to the quantum Yang-Baxter equation. Right. And and this is the story about the R matrix and the quantum Yang-Baxter equation. And finally, the last part is about the quantum symmetric pairs. Again, you can guess that you are going to quantize the classical symmetric pair. Okay, but first of all, let me recall the classical symmetric pair. So we start with a complex simple Lie algebra G, and given an involution on it. Involution means that theta square equals to identity or order 2. And we have a symmetric pair, G and G theta, or a pair of UEA, U of G and U of G theta. And G theta is a fixed point subalgebra of G. Right? And these are the classical version. And and as a quantization, it consists of the U and UI. So U again is the quantum group of the Lie algebra G, and UI is the right co-ideal subalgebra of U. Right? And again, it can be proved that if you take the limit Q equals to 1, this quantum symmetric pair specializes to the classical symmetric pair again. And and the way to construct, by definition, the UI is just a co-ideal subalgebra of U. So the construct UI, it comes with the parameters, certain parameters that satisfy some conditions. So which implies that the quantum symmetric pairs, form a family of, embedding of the UI into U, right? And actually, the subalgebra UI itself is called the I quantum group. I mean, the pair is called quantum symmetric pair, and the UI itself is called I quantum group. Right. So, and why people care this kind of quantum symmetric pair? I think in the work of Gail Lester, her work was motivated by harmonic analysis on the quantum symmetric space. And then the work by Stefan Klopp just generalized this notion from the Lie algebra setting to the Kac-Moody setting. Right. And the case of A to R plus 1. So again, it is the associative algebra over the rational function over Q, generated by 5 generator here, and this alpha I is just range over. It is just from the simple root of the real algebra. Okay, and this generator subject to the following relations, right? So it is a little bit messy. If you look at it, it is lots of condition that needs to satisfy. But again, if you try to compare with the relations from the quantum group, you will see some analogy. Okay. I mean, but for the general setting, the expression may be a little bit cleaner. But when we take the specific case, it is a little bit messier. Right? And as I said, that the I quantum group is just a subalgebra of the quantum group U, and actually there is a very, very explicit way to embed this quantum group to the quantum group. And this, for the type A to R plus 1, this is the way to embed each generator to the elements of U described here. And as I said, that if you take the limit Q goes to 1, this quantum symmetric pair would reduced to the classical symmetric pair. In this case, it is the SL to R plus 2, and with the fixed point subalgebra. And in this case, theta is the it is a linking diagram involution on the A to R plus 1. Right, and let me show you the comparison between the quantum group and the I quantum group. Again, recall that the I quantum group is just a subalgebra of the quantum group. Okay, the first thing is that the quantum group has more rich property. The one thing is that the triangular decomposition, so which is the islet U plus is the generated by E alpha I. For alpha I is the symbol root of the algebra G, and U0 is the subalgebra generated by those K, and U minus is the subalgebra generated by F alpha. So the claim is that this multiplication is an isomorphism of the vector space. So which means that each element of the quantum group can be expressed in a nice way that you can express it as the sum of 3 parts. The first part is the kind of lowering operator, and the third part is kind of raising operator, and the middle part is just those K that act by scalar. And the other one is the classification of the irrep of the quantum group U, and there is the one-to-one correspondence between the finite dimensional irrep of U with the dominant integral weights of the algebra G. Yeah. So these are properties of the quantum group U, but unfortunately, the I quantum group doesn't have these two properties, and it's not also a half subalgebra of the quantum group U. So from this, so the study of the quantum symmetric pair is more challenging than the study of the quantum group, because they lack of the very nice property like this. Right. And all right, almost finally, okay, I will introduce the Schur-Weyl duality, and I will show you how the I quantum group play roles in this generalization. So for the Schur-Weyl duality, it says that suppose that you have the finite n-dimensional vector space over C called V, and U is the UEA of SLN. All right, then you consider the k-fold tensor product of V, and then you have the action of the quantum group on the left, and you have this group algebra acting on this tensor product on the right, and the statement claims that these two actions commute with each other, and they also satisfy the double centralizer property, which means that you can decompose this tensor product as the tensor product of this, where L lambda is the irrep of U and V lambda is the irrep of the symmetric group here. Okay. And in the work of Jimbo in 1986, he quantized this statement, which is like, so right here from the Schur-Weyl duality, you have the action of the quantum of the UEAU, right? And then you quantize it, you get the quantum group. And on the other hand, you have the action of the group algebra, and then you quantize it, you're gonna get the Hecke algebra. And he proved that these two actions are also commuting with each other and also form the double centralizers. Okay. And this can be, generalized further and this work proved by Hongchen Bao and Wei-Cheng Wang. Start with the standard representation V of UI. In this case, it means that I just restrict the standard representation of the quantum group, just restrict to the I quantum group. And yeah, they proved that the action of the I quantum group and the action of Hecke algebra of type B are also commuting with each other, and they are also form the double centralizers. And this is some references. So the first one, by Gail Lester, by the quantum symmetric pairs that I mentioned earlier, and the second by Stefan Kopp, he just generalized from the Lie algebra setting to the Keck-Moody setting. And for the third one, this is the reference for this theorem, and also some setup and light introduction to the quantum group and I quantum group. And the last one is like the survey on the study of the quantum symmetric pairs, and it's kind of showing the recent development on the quantum symmetric pair. All right. Can I have a little bit few minutes?
Sure. Yes. Yeah.
Okay, it's going to be very quickly. And the last notion is about the quantum Casimir operator. So recall that the quantum Casimir operator is a Q-linear map on the U module M, satisfy that it commutes with the action of U, and the eigenvalues are of the form Q to the power some integer right here. And this is on the setting on the quantum group. And the question, I think this is the open question, is that can we have the analogy of this kind of quantum Casimir operator to the setup on the I quantum group? This is still open, and I'm trying to understand it. And actually, I still have no idea what it looks like, but I expect that the quantum Casimir operator for the I quantum group should have the property, these two properties. And all right, so let me go quickly. And there is a notion of unitarized R matrix, right? That which is can be determined by this one. So this Q is the quantum Casimir operator in the previous slide, and this R is, you may think that it is the R matrix, and this is how Joe Kamneser and Peter Tingley define the unitarized R matrix. And again, this is in the setting of the quantum group. And the question is that we are going to try to find the analogy on this notion in the setting of the quantum symmetric pair. So basically we have universal K matrix, which is the analogous to the universal R matrix, and we ask, can we construct something, we may call the unitarized K matrix, and which is analogous to this unitarized R matrix. Basically we just try to find the properties that try to find some property on the I quantum group that emitted from the quantum group. All right, and that's all I have there. Thank you so much.
All right. Okay. Well, thank you very much for this really, I think it was very, very interesting talk for me, I think. Well, it was a bit surprised because at the beginning you mentioned about integrable system, right?
Okay.
Which is actually what I did what I did at my PhD level. Actually, I'm working on integrable systems, but in the classical in the classical case, not in the quantum one. But actually, I came across with this kind of Yang-Baxter stuff, and then this kind of thing, and I kind of familiar with this thing. And so, so what I understand is that the definition of quantization that you mentioned here in this talk might not be the same of what we have in physics, I believe. And it's a kind of it should be the word of deformation, like called Q deformation, right? When you have like a standard group, right, in your in mathematics or in your context, and then you deform it, and then you get you say you get the quantum version of it, right?
Right.
And then with this quantum version, they are no longer now a group anymore, right? They are no longer a group, right? Because they are not satisfy all the properties of that group should have, right?
Yeah.
It does. I understand correctly, right?
Yeah.
Okay. All right. Okay.
Yeah, actually, the notion of quantum group. I mean, there is no precise definition of the term quantum, but it just in the sense that you just you just quantize the classical stuff. That reminds me of the classical mechanics, right? And then you have the quantum mechanics. You put a parameter h, right? And then when you take the h equal to 0, you get the classical mechanics.
Right.
I think that sense in just I think it's just the sense of quantization, something like that.
All right, I get your point. Okay, I get your
point.
But
no one can give the precise definition of the term quantum. Yeah.
I see. If that in that sense, it could it kind of makes sense.
Yeah.
Because in physics, when we talk about quantum stuff, we have h bar. Yeah, we have h bar.
Right.
Planck constant, right? And then when we take the Planck constant to be 1, then we get the classical stuff back, something like that. And then you do the same analogy here, right? You have a Q parameter here, and you take the Q equal to 1 or approaching to the 1, then you get the classical stuff back again. That's okay. This kind of I can't get your point. This is the reason why you call quantum here. Okay. All right. Because actually there is a book called Quantum Calculus.
And then I understand that they also put the parameter Q somehow.
I think that is a thing. I was when I look at it, I was a bit surprised why it's called quantum calculus.
Because I think you got the idea. But I really don't know if this quantum in this context is the same as the quantum is in the context of quantum computer, or I don't know.
Not. Yeah, I don't think so. I don't think that is the same. Really, the same. The same terminology that what we have here in physics, because when we talk about quantum stuff, then we talk about some weird properties of the system, right? But I don't know. It might, because you are in kind of very pure side of science, I would say, math, right? And then you don't care about what really happened. You just follow the math, right? And then you get what you want, something like that. And then
I just follow the production from the physicists, and then I just do math.
But I think it's nice and it's very interesting, because the question is that at the beginning when you define the way that you deform when you put the Q, can you share the slide again, please? And the definition of the bracket of the N.
Okay. One second. The Q integer, right?
Yeah, right. Okay. Yeah, it is called the standard way to define the deformation, right? Or is that another way that you can define the Q deformation?
Yeah, good questions, because quantize it, that there could be another way to quantize it, but the question is that which way is gives you a nice property.
Right.
So that I don't think there is no right or wrong to give the notion to quantize it. You may basically just put the define bracket n equals to q times n, but I think it is boring.
Yeah. Right. So your answer is not. This is not the only way to define the Q deformation. Maybe some other way, but this one is give you some interesting.
Right. And so far I just I just see only this definition of Q integers.
Okay. Okay.
Yeah, because
See,
I think it carries many nice properties, so that's why people
all
use
right.
this one. Mhm.
Okay. Okay. Well, because in physics we also have like especially I don't know whether you know this or not about entropy, right?
Yeah, I know a little bit. Yeah, okay.
Yeah, and then there is a definition of this kind of Q deformation of the Q of entropy is called solid entropy and the Lengy one. And
Mm-hmm.
then there is a parameter in it that is kind of the Q deformation or the standard entropy. And when you take the Q parameter approach to one, you get the standard entropy back. And then for the solid entropy, there is an algebra associated with this kind of Q that you mentioned here.
I see.
I don't know. This is I believe it's more like the same thing that you meant talking
Yeah,
about that
yeah.
stuff.
The one thing that I'm thinking is that the way to quantize is, I mean, to tell that which way to quantize is nice enough is that when you put a parameter q, you get for each q, for each q you get a different algebra, but
Mhm.
for different algebra, if you have the totally different property, like it's like if they look extremely different, I don't think I don't think it is nice. So it's like you when you move q, like one from smoothly. If you let q flow smoothly, the algebra should deform, also deform very nice. But it doesn't matter what q is. It should have the core properties that should hold for any q, something like that. And in the
Okay.
theory of the quantum groups, yeah, as I said, that if you take the q goes to 1, you get the universal enveloping algebra, which is the classical version. But there is the theory called crystal theory, which you take q goes to 0. And the property from that theory, also true for the situation when you take q goes to 1. Yeah, and it's like it doesn't matter q it is, you should have one property that holds for any q. Yeah, that's the nice thing you should have.
Okay. Okay. I
Mhm.
get it. I kind of get it. But okay. When you talk about the R matrix,
Yeah.
and then you call quantum R matrix, right? Is
quantum
that right?
I quantum Yang-Baxter equation.
Yeah, quantum Yang-Baxter, that one.
Yeah.
Um, you actually, I believe it might not. This is a solution of the six vertex model here, which actually
Yeah.
I believe is something to do with the spin model, right?
Yeah, I think so. Yeah, I read a little bit about this literature. Yeah,
Yeah,
very
yeah,
very
yeah, yeah.
shallow.
Yeah. And so I kind of, if I understand correctly, the way the reason why they call quantum because in that particular R function you have a parameter q, right? In the next slide, right? Is
Yeah,
that
yeah, right. Yeah,
the,
let's say on the SL2 case. Yeah.
yeah. That's why it's called quantum, right? Because actually,
Mhm.
this type of sigma-sig model is not necessarily a quantum model. It might be the classical model that actually give you this solution that the Yang-Baxter solution that you mentioned there, I
I
believe.
see.
But yeah, and then another question here because you
Okay.
mentioned about the kind of another way that you can put the R metric with the theta function, right? But you have to modulo it with the f here, and then you give an example in that
Ah,
this
right.
slide. So I think it is the question is how could we know that we should choose the f in this form? Is that any
Okay.
systematic way to pick the f, the right f, and then you get the solution or
Okay.
the R metric
Okay.
back?
Okay. Yeah. So okay, let's see on the SL2 case. If you okay, this is the original version by Drinfeld. Okay, this is, and you see that the theta from the Lustig construction just analogous to the thing in the parentheses. It looks pretty much the same, right? It is a theta from the Lustig construction, and right here, and you take the sum over n, and the other term is the exponential, because and you think that h is kind of the k element, and when k act on the vector in the representation, it just gives a scalar. So it is kind of analogy between the term exponential and the function f tilde, because the function f tilde is kind of weird.
Okay,
but I don't know what's going on behind the scene. It's yeah, but yeah. I actually don't know how Lustig comes up such a construction right here.
That is very good. It might be very a bit tricky to I think the right F. Okay. Anyway, yeah. Okay. So, so I'm not quite get the idea at the last bit of your talk about quantum symmetric pair. I'm not really sure because when you move from the R metric to topic to this quantum symmetric pair, so what you need.
So it is. So sorry. It is not really connected. I'm sorry about that. Actually, so the section of R matrix. My point is just introduce what's going how they use the quantum group to find the quantum Yang-Baxter equation, and the quantum symmetric pair is just another kind of quantization.
I see. Okay.
So yeah. It is just another topic. Yeah.
Okay, I see. So you have a classical symmetric pair first, right? Like a classical pair, and then you do the Q deformation of it, this pair of it, and then you get a quantum version, and then you look at the property again, and then you and I believe that the way that you do deformation is the standard way that you introduce that at the beginning, right? The bracket at the end. Is that the same? The way that you, or is not the same, or the way that you deform your the structure?
Yeah. So far, we use those notation like the Q integer and the Hecke algebra. That's the it's like the basics tools to study these quantum symmetric pairs. Everything based on those examples.
Okay. I see. Very interesting. Okay, at least today I learned why it's called quantum now.
Okay.
I just wonder, well, long time ago, I just why it's called quantum. I don't get it because it's just because well, in physics we also working on this kind of Q deformation a lot, because we need to get a new kind of physics quantities that might be give us more feature or to explain something that we could not understand at the moment. That kind of thing. But I think it's more or less the same. Maybe something overlap here.
Yeah. I think so.
Yeah, but you are more on the abstract side, I believe.
Yeah.
But it's beautiful anyway. Beautiful. I like it. Why not? Yeah, because math, it's beautiful. Yeah. Anyway, I don't know. Is any question from the online? I don't know. Okay. Can you read the question? How should I think of the generator K in the quantized UEA, since it acts more like a group element in the adjoint representation?
Since it acts more like a group. Yeah. Okay. As an element of the quantum group, so it is just an element, right? But as an operator acting on the vector space, Yeah, again, you may think that okay, it depends on the representation. For the standard representation, it is just act by scalar. But for the adjoint representation, I don't have any insight way to think about it, because just follow the definition of the adjoint action. I'm sorry about that.
Okay, that's fine. Okay, that's fine. Okay, that. Okay,
Secondly,
another one. Okay. Can I relate the representation that you talk about in the Yang-Baxter context to some representation of the bread group? I think so, right? Because Yang-Baxter is somehow, is this related to kind of the way that you bread your
right. My impression is that they have the same model. Because even in not theory and bread group, they could form the Yang-Baxter equation, right? And we can use the solution. We can use the quantum group to find such a solution. That's my impression. That because the Yang-Baxter equation can come from many ways. Like one can come from the problem in knot theory, one can come from the representation of bread group, and etc.
Okay.
But sorry, I didn't know in detail. But
all right. Okay. Okay. Any more question online from the online? No. Okay. That's all I think. Well. Okay. Anyway, I think okay. So I think it's about time because we we spend quite good. I mean, hour and a half, I would say, for this. And then before we leave, please for the audience, online audience, please tell us to complete the survey form here, which is actually the link given there. And you can give us any comments, and then we can use that your comments to improve our activity next time. And then I would like to thank Korkeathikhun again for this wonderful and very nice talk and about this quantum
you're
group.
welcome.
All right. Okay. Anyway, okay. I think see you again for next if Colloquium number 16 next month. I mean, next year actually, after New Year. Okay. Stay tuned then. Bye. Thank you very much. Bye.
Thank you. Bye.